Hello everyone, my name is Salman Parvez. I am a faculty member at Rochester Institute of Technology, Dubai campus in United Arab Emirates. The study I'm going to present today is about the tapping process of TI6 using finite element simulations. The presentation summary is background, motivation, what is tapping process, aims and objectives, numerical methodology, results and discussion, then conclusion and the futuristic work. If I talk about the background of this problem, so tapping operation is one of the most complex metal cutting operations because it has an intricate cutting tool geometry. Then it is widely adopted in the automotive industry because several components require internal threading. One of the major thing that was available in the literature is that chip load in this process is a complex function of the position, and the total load can be divided into two portions, namely base load and the chip packing load. So base load is generally comes from the formation of chips and the friction involved in the cutting. However, chip packing load comes from the chip clogging. And interestingly, chip packing load is very complex function of the geometry and can be 5 times of the base load in some cases. That makes this process even more complex. If I talk about the motivation involved in the work, so definitely tab geometry controls the cutting forces and the cutting torque. Cutting forces and cutting torque, in some cases when it's higher, can break the tool, can break the tab, and can provide a very high tool wear at the cutting tool. Understanding the torque formation will help us in optimizing the tapping process and provides better understanding. Similarly, there is available, like if we talk about the literature available in metal cutting, so most of the literature is focusing the conventional turning, drilling, and milling operations. But when it comes to the intricate cutting tool, like in the tapping operation, there is a very limited uh, data available or literature available. So in the current study, we try to perform the tapping operation using finite element simulation related approaches. If I talk briefly what is tapping operation, tapping is a process of cutting internal threads with a multi-point threaded tool, which is called as a tap. Tap is a fluted threaded tool used for the cutting of threads, and tap generally enters the workpiece material axially and cuts threaded profile on the existing hole that was generally produced through the drilling operation. Tapping is generally conducted at a very low cutting speed. Aim and objective of this work is that it is a common observation in the metal cutting industry that most of the times cutting tap results in breakage, specifically when the magnitude of the torque is very high or the cutting force is very high. The current study is aimed on the investigation of of the tapping process using TI6 as a workpiece material. TI6 is regarded as a difficult to cut material because of its high hot hardness and the low thermal conductivity. So that makes the tapping even more complex. If I talk about the numerical methodology adopted in this work, we have utilized Advantage as a software that is provided by the third wave system. Software can execute coupled thermomechanical transient analysis and can provide adaptive rematching techniques to the chip for the chip formation. In order to model the material, we have utilized Johnson-Cook material model. Johnson-Cook material model is based on 3 parts. So the first part with constants A, B, and N governs the strain hardening behavior. The second part with the constant C represents the strain hardening sensitivity of a material, and the third term with temperatures address the thermal softening. So all these constants can be obtained from the material testing, like tensile test or compression test. However, they are widely available in the literature as well. So for this work, we have taken these constants from the literature as mentioned in the references. So this slide shows the CAD model of the tap. The tap was basically M10 1.5 configuration, and it was generally modeled in the Autodesk Inventor software. Again, the dimensions are widely available in the literature, so we have utilized these dimensions to model the CAD tap. Then this is the CAD model when it is transferred into the software. This is the workpiece geometry, and this is basically the tab geometry when it was transferred from CAD to the GWS Advantage software. Again, the advantage utilize explicit Lagrangian and adaptive remeshing approach to perform the machining simulation. This slide shows you the mesh model of cutting tool and the workpiece geometry, and these are basically the parameters that were adopted. Those parameters were adopted for the TI6AL4V modeling, and again they are available in the literature, so we can easily get these values from the literature. This table talks about the DOE constructed for the study, and it can show you, for example, the parameters that what was the thread pitch, what was the tool material. Again, we utilized four different values of the cutting speed because this study was more focused on the cutting speed variation. Simulation was run, each simulation was run for 360 degree rotation, like one complete revolution, and this is when the process was stable. However, this was very laborious process, very tedious process, and each simulation required 9 to 10 hours approximately duration. Approximate duration, and these are the different sizes which were utilized in the simulation work. So if I talk about, for example, this is the one of the simulation. So that shows the rotation. This is the top view of the tool in the hole, and this shows 0 degree, 116 degree, 32 degrees, and 360 degrees. This is the cutting force signal obtained in the x direction, x-axis, and it was a lot of fluctuation. So in order to utilize it properly, what we did, we took the absolute value, we converted it into the absolute value, and then we took the average of the forces, just to have a good comparison. So if we plot these values, we can easily see that the values in the x directions are much higher than the x and y plane, x and y axis. So x and y plane is just like a plane of where the workpiece is oriented, where the tool movement in the z direction. So it was obvious that because of the higher contact and the engagement with respect to the chip load, higher value of force is present here. And other important thing that was observed here, that cutting force most of the times increasing and then it starts decreasing. So the initial increase in the cutting force was linked with the strain hardening phenomena. However, at the lower end, when it starts decreasing, this is the result of the thermal softening phenomena. And this is available in the available literature as well. If we talk about some of the conclusions and the future work involved in this work, so again, tapping process is very difficult if you try to do the analytical model for the process. So finite element solution is a good methodology, but again, at the end, it's very time consuming and resource consuming. So it is very difficult in terms of computational work involved. If we talk about decrease in the cutting force at the higher value of the spindle speed, it can be linked with the thermal softening phenomena. And another reason for decrease in the cutting force is because at higher cutting speeds, the coefficient of friction decreases at the interface. So coefficient of friction is associated with the sliding speed, and it generally reduces when you increase the cutting speed. Higher forces were observed during the initial part when we increased the cutting speed, and that was linked because of the work hardening behavior or strain hardening behavior of the material. Increasing in the torque and the force values with increasing cutting speed is also the representation of the chip clogging action, and it can be controlled by the chip geometry. That's all at my end. If you have any questions, please feel free to ask me. And thank you for your attention for this work. Thank you once again.